everybody. So today we are going to start chapter 16, and chapter 16 talks about, is our beginning of our discussion of kinetics of rigid bodies. And what we mean by kinetics of rigid bodies, kinetics, as you recall, the two sciences of kinetics and kinematics. In kinematics, we look at sort of the geometry of motion, the way it looks, and we talk about position, velocity, and acceleration, but we don't really talk about what causes those things. We just talk about the way it looks. And in kinetics, we start to deal with the forces and moments that cause motion. Now, rigid bodies as opposed to particles, we're talking about situations where we need to address the shape and the size of the body. So we are also going to be working with the idea of centers of gravity or centers of, centroid centers of gravity, and continue with our discussion like that. So the only two sections that we're going to cover in section 16 or in chapter 16 are sections 16.1 and 16.2, and each of these sections is actually broken down into subsections. So in section 16.1, we have sections 1E through 1F, and we're actually going to skip section D. So we're leaving out quite a bit. We're going to talk about the most important, sort of the foundational material for this, and give you a couple of homework problems, and then scoot on to section 16.2 tomorrow, or in our next lecture. All right, so having said that, let's come over to the PC and take a look at the PowerPoints. There are quite a few PowerPoints for this particular section, and there's a lot of topics. But once again, these are the PowerPoints for the entirety of section 16.2, including those omitted sections or subsections. So in chapter 16, there are only two sections, but like I said, some of the subsections will be omitted. So the first part of this is we always go back to Newton's second law, force equals mass times acceleration. It's like the basis for everything in kinetics in our entire life. And the other equation is sort of directly built upon that idea, where we also have the summation of moments on a rigid body is equal to the rate of change of angular momentum. Now, the important thing to notice here is that when we talk about these moments, we always have to say for moments and angular momentum and rate of change of angular momentum, we always have to state where we're taking the moments about, where we're measuring angular momentum from. So the sub G here refers to the center of gravity. So what we're saying is the summation of moments about the center of gravity, which would be the external moments, is equal to the rate of change of angular momentum of that rigid body about its center. And same here, when we take a look at Newton's second law, we have the summation of forces, which once again it's a vector, but those are the external forces that are acting on the body, is equal to the mass times the acceleration of the center of gravity, but that's what the bar over the A means. So we're talking about the acceleration of that center. All right, so the next thing that we kind of mentioned for the first time is D'Alembert's principle, which is basically what we're talking about here. And we're going to just prove that the external forces acting on a rigid body are equivalent to that inertia vector, MA, and that the mass center in the couple of I alpha. All right. So this is just that idea of moving forces, transmitting forces on a rigid body to another point, and expressing forces as a force plus a moment is really what we're talking about. And we did that back with rigid bodies previously when we were talking about couples and force couple systems. So this is just extending that idea to something that looks three-dimensional. Now, I want to assure you, we look at three-dimensional looking bodies, but in chapter 16, we're really not going to get into three-dimensional motion. So we're always talking about motion of a three-dimensional body that has enough symmetry, like from front to back, that we don't have to consider the third dimension, or we just talk about a slab of a rigid body that is two-dimensional. So, but in some way we simplified the discussion. We will touch a little bit on fully unrestrained three-dimensional motion, but it's one of those, somebody told me one time, it's like, how does a chicken cross the road? Or if a chicken needs to lay an egg in the middle of the road, the way the chicken needs to do it is to get in, do the job, and get back out again. So it's one of those things where we don't want to spend a lot of time wallowing in it, because there's just a lot of things that can confound the situation and not result in good teaching at this level. So when you really get into three-dimensional stuff, you need a computer to help you model it. So we can touch on it and look at some specific cases, but one of our attacks with three-dimensional motion, especially unrestrained general three-dimensional motion, is to decide what we can eliminate from our mathematical treatment and still come up with a good solution. All right, so when we're talking about the equations of motion in a rigid body, what we're basically doing here is just what we did mathematically on the slide before. If we have a bunch of forces acting on a rigid body, we can say that that has some relationship to an inertia vector acting at the center of gravity where such it might be, and that would be the translational motion piece. Then in terms of the rotational piece, the moments created by those forces are going to be relatively equivalent or equivalent to the rate of change of angular momentum vector about the center of gravity, if all of these forces are also taken about the center of gravity. All right, so here we go where we talked about that really general piece, and now we're going to come back to general plane motion where we're talking about the slab. Or, I could think of this, I always think of these as being like home-cut potato chips, like just a chunk of a potato, and we have the whole potato now, we've just cut a slice, a big thick slice, but the slice is symmetric, so we're looking at it in two dimensions. That simplifies not only the motion, the velocity, and everything else, but it also means that mathematically all of our vectors of translation, our R and V vectors, are all going to be in that plane, and that makes our alpha and our anything rotational in the pure Z direction. So it simplifies us from essentially 9 equations to 3 equations. So the simplification is pretty significant. All right, so when we talk about angular momentum of that slab, we go ahead and compute that, where we just take that R times the momentum vector, the linear momentum vector, the Vm momentum vector, and when we go through the math, we find out that that's going to become equal to the moment of inertia about the center of mass, or the centroid, times omega. Okay, and omega is that rotational velocity. So after we differentiate that, then we know that the derivative of omega is alpha, or rotational acceleration. So we can say the sum, or the angular momentum about the center of gravity, is equal to I omega about the center, and that the rate of change of angular momentum is equal to I bar alpha. Okay, so the results are valid for plane motion of bodies which are symmetrical with respect to the reference plane. It's just my slab-o potato. And the results are not valid for asymmetrical or three-dimensional bodies. Once again, it's the same idea, we just need lots more equations. Okay. All right, so what this D'Alembert's principle just tells us how to translate this. If we're talking about X and Y, how do we what do we do for that? Well, if we're in plane motion, once again, we simplify this to the 3 equations. We have summation forces X, summation forces Y, and summation of moments about the center, which are all going to be G. So we don't really even have, or excuse me, all going to be Z. So we don't really have to specify the direction. We just know that the moment, all the rotational stuff, is going to be perpendicular to the XY plane, which defines it as being in the Z direction. All right, so if we take a look at this, we have a rigid body and we're moving, we have a force acting on it here. If we move that force along its line of action, we're able to use the principle of transmissibility to say that that is the same in terms of the linear motion of that body. It may change something about the moment, which we need to take into account by taking a look at something like this, okay? So, I don't really want to get into that. Let's get into solving a problem, because it's a little more interesting than looking at slabs of potatoes. So let's look at this perfectly symmetrical, full-size transport van, right? So what we have here is a van that is moving with some speed, 30 feet per second. Truck brakes are applied. So would you guys call that a truck? I would call that a van. I don't know, but truck is a word that we use interchangeably. But with this, what's that?
It's a cover truck.
A cover truck. Okay, I like it. So on the cover truck, we're moving forward with the speed of 30 feet per second. The truck brakes are applied, which means that we're going to have a frictional force on the tire between the tires and the ground, and the wheels will stop rotating. That means it's in a slide. It's observed that the truck skids to a stop in 20 feet. Okay, that means that we have some sort of an acceleration. If we consider if the truck is moving forward, which we hope it is, because if it's going 30 feet per second backward, that's a trick in and of itself. But we're going to come to a stop in 20 feet, and we want to find the normal reaction and the friction force at the wheels. All right, well, like every good dynamics problem, we start with force is equal to mass times acceleration. That's right, AJ's mouthing the words. It's true every single time. Newton did so much for us. So we're going to go ahead and draw a free body diagram, and we're going to get the equations of summation forces x, summation forces y, and summation moments about the center of gravity. And the trick here is we really hope there's no alpha, right? This thing can decelerate. We hope all of the acceleration is in the transverse direction, in the x direction, because if we're rotating, we're going to go tip over, head over tails, or tails over head, which is not a good idea. All right. So, just like any other good problem, we start with a nice force diagram. The only thing that we need to recognize, we have forces acting on the wheels, normals and frictional. We have the weight. The weight of the van or the weight of the cover truck will operate from the center of gravity. And we know our velocity, and we know the distance that we take to stop. Now, this is going to be a little kinematic solution. We're going to use a kinematic equation to determine the acceleration, and that means that we're assuming that that acceleration is constant. So in other words, during the entire time of this 20 feet, we are going to be decelerating or negatively accelerating from 30 feet per second to 0 feet, and we're doing so at the same rate. So if we do that, we can solve for the acceleration, and since the truck is not tipping, that is the acceleration of the mass center. It's the acceleration actually of every point on the truck. All right, so then we do the equation summation forces x, summation forces y. In the y direction, we have normal forces and we have the weight, and there's nothing going on. We're not crashing through the pavement. We're not levitating into outer space. So the acceleration in the y direction is equal to 0. But in the x direction, we have a little bit more going on. We have the force of friction, and then we have the mass times the acceleration of the mass center, which, since we're slowing down in the positive direction, is negative. So using that idea, we can solve for a coefficient of kinetic friction, and that value is almost 0.7. Okay, once we do that, we know what the coefficient of friction is. That means that we can determine what the friction is going to be and then what the normal forces are. Now, if you think about it, there's no reason to think that the weight being borne on the front tires is the same as the weight being borne on the back tires, is there? I mean, if the engine is far forward, there's going to be more weight, and also that acceleration, as we brake, is going to put more force onto the front, right? So things are going to start to come up a little bit in the back, or the other way around. Think about this. If you had a covered truck and you started to slow down and you had a great big package in the back that was on a frictionless surface or a low friction surface, what's going to happen to the package? It's going to come forward, isn't it? So, because as you're starting to slow down, the package has to have something to help it slow down. It's still going at that particular rate. All right. So then we talk about the summation of the moments about some point. If we're trying to find point A or point B, we can sum those moments about the front tire or the back tire, and we can solve for the normal force on the rear, and the frictional force on the rear, the normal force on the front, and the frictional force on the front. And the one thing, if you take a look at the normal forces, the normal force on the front in this situation where that cover truck is braking is essentially double the frictional or the normal force on the back, isn't it? That just means, and you can feel that. I mean, if you're slowing down rapidly in a vehicle, you know that more weight is being shifted to the front wheels. Or if you've ever had the pleasure of driving a trailer, do you guys pull trailers effectively? Are you guys good at that? Have you ever pulled a trailer?
Yeah.
I hate pulling trailers. The one thing I despise almost as much as anything I see on the road is a U-Haul trailer being pulled by a tiny little car. It's like, that is just a horrible situation. But you have to load those trailers properly, right? So that when you brake, you don't have this thing where everything goes apart and all the weight comes off the hitch and you lose control of the whole situation. So, but you guys are all talented at this, so I'm not worried about you. All right?
So is the W like
the weight, yeah. And you know, if you knew it, I mean, so you just plug that in. But so yeah, so if you look at that, whatever the weight is, the rear wheels are bearing, the normal force on the rear wheels is about 17%, 17.5% of the weight. But on the front wheels, it's about 32%. So like I said, nearly double on the front what it is on the back. Yep. So any of these problems, always start with a good free body diagram, that good analysis, and then you can see that you have almost all of the skills that you need, you've been taught previously to solve these kinds of problems. All right, so we have a thin plate. Once again, that's key for symmetrical, going back into the page. 8 kilograms held in place as shown, neglecting the mass of the links. So these are free. You don't have to put a G in the middle of them with a weight. They're asking, when you cut this wire up here between H and B, what's the acceleration of the plate? It's going to rotate down that way, right? And something's going to happen in the links. There's going to be a force born. You're either going to put the links into compression or tension. So the force is going to be directed along the links. Okay. So we talk about after the wire's cut, all particles of the plate are moving along parallel circular paths. That's the constraint of this sort of a situation. Where you have two links like that, we're not moving in the same, we're along concentric, I guess. What did I say, concentric? They're parallel. They're not concentric. They're parallel circular paths. So point G is moving along the same sort of a path that is a curvilinear translation, and it's going to be parallel to a circular path described by any other point on the plate, including points A and D. It's not true for the links in general. It's just true for the points A and D because they're also on the plate. All right. We also know that the force in the links are going to be directed along the links. It's either going to be tension or compression. So from our analysis that we've done previously, either in this class or some of you who've done method of sections or method of joints in mechanics and materials have seen this sort of analysis before as well. So here we're going to be talking about the forces. We're going to measure a tangential direction. In other words, this is sort of a trick. I don't know. If I were to do something like this to you on homework, which I wouldn't, I would suggest this to you. Okay? So in other words, because it's a circular path, it's much easier to analyze this using normal and tangential components of velocity than it is to analyze an acceleration than it is to do using X and Y, even though we definitely have XY plane. But if we do normal and tangential in the XY plane, the math turns out to be a lot easier. So we're moving in the tangential direction, so we have to find the component of the weight because the weight is acting in a purely Y direction. So we find that, and that's equal to the mass of the plate times the acceleration of the center, which is the point we're analyzing. So the acceleration of the center is the same as the acceleration of the acceleration of the center is the acceleration of g at that particular instant. All right. So continuing then, we can take a look at the moments. Same thing, if we're going to do those same directions, we need to break it up into normal and tangential. What that allows us to do is to set everything equal to 0, in the sense that when we're just starting to move, we're going to be, wait a second, what are we doing here? Hang on, let me look at this. This is bugging me for a minute. FA, sine 30, so we're going, oh, we're just taking, this is just moments. Okay, so we're not talking about doing normal and tangential. In this case, we're just remembering that moments are just all, we're taking a force and its perpendicular moment arm to the center. So the first part, FAE times the sine of 30, is the vertical component of this force. And then the 250 is the horizontal component of this to get us back to the center of gravity. So once again, we're just summing the moments about the center of gravity, and so we're just taking the perpendicular components. Now, we have FAE times the sine of 30, which is the vertical component, times the horizontal distance, and then we have FAE times the cosine of 30, because that's the horizontal component, times the vertical distance. So in other words, we've done both the forces here and here. We have summed those in that particular way, and at that point, what is the moment of the center of gravity? Well, it's equal to 0 because g is at the center of gravity. So we sum those up, and we have two equations, and we have two unknowns, so we can solve for FAE and FDE. Yeah, so that's kind of an interesting. The problem is fairly straightforward, but they change. They change the reference frame. They change from, which makes perfect sense, but they change from a normal tangential to everything's in the z direction, like I said before. So then they sort of go to an x and y component of the force and moments, which makes sense. There'd be no reason to keep it in some other direction. If you use this whole force, you could use the whole distance between here and here that's perpendicular to that, but that would require more trigs. So this is a nice, easy way to get it simplified in a hurry. All right. This is the last example problem that I'm going to do before I do one from your textbook. So here we have a pulley, and as you see, we have an internal pulley, and we have an external pulley, and we have two different weights. We have a 10-pound weight B that is spun around the inside pulley, and a 5-pound weight which is spun around the 10-pound pulley. So in other words, we have weights, and then we also have a rotational acceleration for this pulley, because both of them are going to create an alpha around the center, and the center is definitely also the point where everything's going to happen, because it is secured. There's a fastener at that point. All right, so we're going to assume that there's no axial friction. We want to determine the direction of rotation. In other words, this 10-pound weight, both of the weights are going to be pulling down, but A is going to tend to make a clockwise moment, B is going to tend to make a counterclockwise moment. So which one is going to win in the battle of the moments? All right, so we do summation moments about G. We have 10 times the radius of the smaller pulley, 6. 5 times the radius of the outer, which is 10. And so what we find out is that we have a bigger moment from this. This is 60 and this is 50. So that means that this one's going to win and the rotation's going to be counterclockwise. So there's an interesting little sum right out of the chute. Then we can use our tables in the textbook to find our I-bar. Now, mostly we've worked with moments of inertia of area, and we're not going to get anything really complicated in terms of solution, but it's important to note that here we're talking about a mass moment of inertia, so the dimensions are a little bit different and the formulas are a little bit different. So you just have to, they're still in your textbook, but instead of using pure geometry in terms of all lengths, we're using a mass and a length squared, okay? So we find out what the I-bar is, and then we know that the acceleration of A is equal to R times alpha. And the acceleration of B is equal to a different r times alpha. And since they're both about the same center, in other words, the outer pulley and the inner pulley are both about the same center, they're going to have the same rotational acceleration, aren't they? They're not going to have the same translational acceleration, maybe, but in terms of alpha, they're going to be the same. So we can use that equation and solve for alpha. And then we can break that down and find our accelerations because they're both going to be equal to r times alpha. So we have different r's. And it's kind of like almost a gear ratio problem where the accelerations are going to be proportional to the relative size of the gears or the pulleys in this case. All right. At this time, do you guys have any questions? All right, well, let's work a problem. I have, let me pull this up. I assigned you 2 problems, and I'm going to work, I don't know if I'm going to have time. I'll do at least one. But I have 2 problems that I'm going to work that are very similar. So the problem in your homework is problem 16.1. And basically, you have a thin panel on a truck right here. And it's actually the same setup for the problem number 2, which is I'm going to work in class. You have a length, you have an angle, and here we have A resting smoothly here on a rough horizontal surface. That's code for friction, right? So you're going to have a frictional force, which is a good thing. Otherwise, it would slide down, and there would be no problem. It would just be laying flat on the flatbed. And B is supported by a smooth vertical surface, so that means no friction here, right? All right, knowing that the deceleration of the truck is 12 feet per second squared, determine the reactions and the minimum required coefficient of static friction here at A. All right, in part 2, we have a very similar problem where we have that uniform plate. We have a rough horizontal surface and a smooth up above, and we know that the panel remains in the position. Okay, that means it's not going to rotate at all. So we're going to determine, this time, the maximum allowable acceleration. So in other words, if we go too fast, the plate's going to slide down. It's going to overcome the friction, and the weight of the plate is going to drag it down so that it will be lying flat on the flatbed. So what is the most acceleration that we can move forward with in order for that not to happen? And then the second is what's the corresponding minimum required coefficient of static friction here at end A. All right, so we've got a little bit of stuff to build on here and a little bit of new stuff. So let's take a look. Well, the first thing that we want to do with anything like this is to draw a free body diagram. And our interest here is in the plate. I'm going to turn this, no, other way. Get some. Okay, so this is the plate. What do we know about the plate? We know that it's 5 feet long. And we know that we have friction here. And if the plate wishes to slide that way, friction opposes motion. Right? And then we also know that resting here, there's going to be a normal force, meaning that the flatbed is going to be pushing back up. And we're calling that point A. So I'll call that the normal force at point A. All right. Now here at the top, we don't have any friction. So I can say the force of friction here at B is equal to 0. But we still have that normal force. So we have a normal force acting here at point B. And since this surface is vertical, the normal force here is going to be horizontal. And here it'll be the opposite. All right. So if we start thinking about this as being a rigid body, in the past we might have ignored the weight of the plate, but now we have to take that into account. And so if this plate is 5 feet long, we know that the weight, if it's homogeneous and has all those properties that make us able to analyze this in 2 dimensions, that's going to happen right at the middle along the plate, and that the magnitude of that weight is 60 pounds. All right. Excuse me. All right. The first thing that we can see, which is kind of a, am I going to say that? Now, if we have a force of friction here, oh, I see. Okay, I was just trying to think about something here. Let's take a look at our forces. If we sum forces in the x direction, and we sum forces in the y direction. All right, let's take a look at that. In the y direction, the plate is not going to be moving up and down, right? So that's going to be equal to 0. Now, in the x direction, that is not necessarily true. This is going to be equal to something else, right? It's going to be equal to mass times the acceleration of that center. All right, so if we take a look at the x direction, we have 60 pounds acting downward. We have the normal force at A acting up. And those two things added together equals 0. So that tells us that the normal force at A is equal to 60 pounds. Right. Now, in the x direction, I wonder if I want to do something different here. What I'm really interested in is I don't want this thing to move here at point A. All right? So the first thing that I would like to do is to do a summation of moments about point A. And what I'm really hoping for is to, let's just determine what those values are. So here at A, we have a 60-pound force acting on point A, or not on point A, but we have a 60-pound gravitational force, and then we also have, that's the only thing we have really. What about this one? I'm thinking about something going on here at point B, about the normal force at point B. I just want to, there's no frictional force, but there's nothing going this way, all right? But,
isn't there like the acceleration of the truck?
yeah, we're going to have the acceleration, which is actually going to be going this way. The mass times the acceleration of the mass center, which is the inertia vector, right? So we have an I bar alpha. But the thing is that we want this alpha to be equal to 0. Right, in order for it, because we're asking for what is the maximum acceleration for it not to spin. All right, so if we just, but there's something that's bugging me about this. It's this. Anyway, I will talk about that in just a moment. If we take the summation of moments about point A then, all right, let's just take a look at that. Let's just look at the moments. And if we look at that, if we take the 60-pound force from the weight, okay, and then, let's see, what's my angle here? 60 degrees, okay. So this force is vertical, so if we take the horizontal distance between there and there, that's 2.5 feet. But if this is 60, it's times the cosine of 60 degrees, right? There's something that's, I can probably tell. I'm not very good at hiding my emotions. There's something that's bothering me about that. But that's 0.5. So the moments then, which are going to be counterclockwise, are going to look like this. And we get 60 times 2.5 times 1/2. Is 75 in units of foot-pounds. All right, so that's, let's just say that that's the moment of the, that's just the moment from point A. Now I'm kind of ignoring this for now, and I'm going to talk about it in just a minute. All right, so what is this going to be equal to? Let's just go like that. That's going to be equal to that I bar times the accelerator. Let's just say this is equal to force times distance is equal to I alpha. All right. Now, the thing that's bothering me is this. Okay. If this slips, at the moment it slips, the normal force at B is going to be equal to 0. All right, so what does that mean? Well, that isn't true while the plate is sitting still, but when it starts to move downward, it's going to be 0. So we're setting the normal force at B equal to 0 as that constraint condition for when the plate starts to move. Okay? I don't like that because it feels a little inconsistent to me, but it's the way that we're going to be able to determine that. It's not mathematically inconsistent. It's just that we're talking about two things. We're saying, well, it doesn't really slip, but right when it does slip, the normal force turns to 0. So we're just setting it as a limit. All right? I can live with that idea. All right. So anyway, let's continue with that thought. So then if we have the summation of moments, because if this is equal to 0, then this is the only thing. If NB equals 0, let's say that will be at slip. So that's what we're setting as a limit. Then this is going to equal R cross F, right? Or it's going to equal I alpha, depending on how we set that up. Let me go back here and take a look at something here. Okay, so what we're basically saying is the summation of moments about point A is equal to the angular momentum rate of change about the center of gravity, and that's equal to I bar times alpha of the center of gravity. Now see, the part that bothers me about that is we're still talking about that condition right before alpha starts. And so we're still talking about that being 0. But if we set it as a limit, we can kind of work with this a little bit. All right, so if we set this, and then we say, if we take the mass all right, let's just do this. What is that? That's equal to this. Here's my inertia vector, I guess, is what I'm saying. So let's set this equal to, see, I don't like the way this equation was developed here, so I want to go back and take a look. Maybe I should show you guys the camera, the podium PC. All right. All right. So got that hg. Force is equal to mass acceleration. That results are valid for plane motion, which are symmetrical. Right. mg is equal to I bar alpha. That's where I keep coming back to in the discussion. I bar alpha. Okay. But the answer is that we don't really have any alpha in this problem. So what we need to do is to think about the summation of moments as the summation of moments effective. Okay, so this is where I want to go right here. All right. So if we then take a look at this equation, we say the summation of moments about some other point A, which is what we're talking about, is equal to the summation of the moments effective. Because we don't really have an alpha here, we need to think about that as the moments effective. And what is that value? Okay, well, if we're talking about point A, we're going to be talking about a moment arm, which is an R, crossed with that inertia vector, which is MA. And this is, oops, you can't see what I'm writing here. Okay, so this is just like with the cover truck. All right, so we're talking about the summation of the moments, I'll write this out, about point A, are going to then equal the summation of moments about A effective, which this is the 60 times 2.5 times 60, cosine of 60, equals RMA. And this is what I'm looking for. Okay, now I feel like does that make more sense? All right, because when you can't get there from that discussion of rate of change of angular momentum unless you break this down into those effective moments as well. All right, so then we have 60, 2.5, and this is a half. Then we have R, which MA is horizontal, so we need the vertical component of the moment arm, the distance from here to here. So R is 2.5, in this case, times the cosine, or the sine, because this is the opposite, the sine of 60 degrees, okay, times the mass, which we don't have a mass, but we are given a weight, right? So if this is 60 pounds, that's going to be 60 over 32.2 slugs, right? So we have R mass, which is 60 over 32.2 slugs, times the acceleration of the mass center. And that's because it's going to give us that limit, all right? So if I write this out, I already found this value, which is 75 foot-pounds equals the sine of 60 degrees is 0.866. Multiply that by 2.5. That's my length from here to here. Rather, that vertical. Then multiply that by the number of slugs, which is 60 divided by 32.2. And that value is 4.034 times A bar. And this is going to be in slug feet. So if you get a pound per slug, that actually turns out to be a foot per second squared. All right, so we get A bar is equal to 75 divided by that number. So my acceleration is 18.6, and I have foot-pounds per foot slugs, and once again, from force is equal to mass times acceleration, weight is equal to mass times gravity. Weight of slugs, weight of pounds divided by mass of slugs is equal to G, which is in feet per second squared, just showing the dimensional equivalence of a pound per slug. So it's 18.6 feet per second squared is equal to the acceleration of the mass center. All right, so the first question was maximum allowable acceleration of the truck. That gives us that limit because we've set the normal force at point B equal to 0 as a condition for initial slip, and we have essentially set the alpha of this point to be 0. So we've set those. Do you see how those are not consistent, though? I mean, this is 0 right before it slips. This is 0 right after it slips. So we're using it kind of like a limit. And that, I shouldn't have got into it too much, but that's what's bugging me about it. But it's a limit. It's okay. It's going to be a little bit off, but it's not the numbers. It's it's philosophically that bugs me a little more than anything else, but it's still okay. All right, so we want to determine that is the maximum allowable acceleration, the corresponding minimum required coefficient of static friction. Okay, well, if we go back to our summation of forces in the x direction, we know that in the x direction, then when this slips, that's going to be the only force, equals mass times acceleration. So my mass is, once again, that 60 divided by 32.2. Okay, and then my acceleration is the 18.6 feet per second squared. So slug feet per second squared is a pound of force. So if I multiply those two numbers by each other, I get, does that look right? 34.6 pounds of force. Okay, that means I need to have 34.6 pounds of force here. And I know that the frictional force is equal to mu s times n. So that means that the frictional force, 34.6 pounds of force, is equal to that minimum mu sub s that I need times the normal force at point A, which I found to be 60 pounds. So my coefficient of static friction is 34.6 pounds divided by 60 pounds. And that value is 0.577. So I have to have a pretty rough surface, right? I have to have 0.577 as my coefficient of static friction in order to keep that plate from sliding under those conditions. All right. So do you guys have any questions about this? All right. All right, well, that is it for today, and I apologize I've kept you a little bit late. But I will post this video as soon as they process it for me, and I will look forward to seeing you on Friday for our second and final discussion of Chapter 16. So you guys have a good day.